So good morning and welcome to lecture number 8. Last class we discussed about pipelining. We did explain you the 5-stage pipeline. Just to recap, we had 5 stages in the pipeline, namely the instruction fetch, instruction decode, fetching the data for the instruction, executing the instruction and writing back the result. In the instruction fetch stage, the instruction is actually fetched from the memory and then the program counter is incremented. In the decode stage, the instruction that was fetched is basically decoded. Then the data that is necessary for the instruction to execute is fetched in the DF stage. Then the instruction is executed. Then the results are stored back. And then we did see that the hardware that is responsible for doing decoding or any of these stages, they are independent of each other. So when you bring an instruction and then when it is decoded, all the remaining 4 parts remain idle. While I am fetching the data for instruction, the remaining 4 parts remain idle, and so on, so forth. So one of the motivation was that why can't we use every bit of this hardware all the time, and that resulted in what we call as the 5-stage pipeline for instruction execution. So last class we did see these stages, and we did also understand that we will have registers in between so that these stages are isolated. So let me assume that there are, say, 3 instructions. The I1 is fetched. When the I1 is decoded, I2 is fetched. When the I1's data is fetched, I2 is decoded, I3 is fetched. When I1 is executed, I2's data is fetched, I3 is decoded, and so on. So that means that there are more than one instructions that are executing at the same time. They are in different stages of execution, but one follows the other. And this is where we stopped last time. And we did also mention that between every stage there needs an isolation. For example, when I1 is getting decoded and when you are fetching I2, the data that is got because of the fetch of I2 should not affect the decoding of the I1. So there needs an isolation between every stage, and that isolation is basically achieved using what we call as registers. So we stopped at this point. We also mentioned that what we mean by this RTL or register transfer level. As you see that the execution of the instructions can be modeled or can be described as moving from one register stage to another register stage at every clock cycle, and so this basic description of instruction execution is at the level of what we call as the register transfer level. Okay, now let us go and see what are the challenges in building up such a pipelined architecture. Now let us take 2 instructions, say add R1, R2, R3 and multiply R4, R5, R1. This instruction does it, and this one does. Note that these R1, R2, R3, R4, R5 are registers. This instruction add R1, R2, R3 essentially adds R2 and R3 and stores it in the register R1, while your multiply R4, R5, R1 multiplies the contents of R5 and R1 and stores it in R4. Now let us see how these instructions are going to get executed in this pipeline. Let me call these instructions by I1 and I2. First, I1 is fetched. When I1 is decoded, I1 is fetched. When I1 is decoded, I2 is fetched. So let us take this as the timeline. When I1's data is being fetched, when the I1's data is being fetched, I2 is decoded. When I1 is executing, that is when our content of R2 and R3 are getting added, the question now, please note down, can we fetch the data for the instruction I2? Please note that since mul follows add, the value of R1 is nothing but the result of the addition operation in I1. To repeat again, the value of R1 which this multiply instruction is going to take should be the result of the addition in the instruction I1. Now, when the I1 is actually getting executed, that is still the latest value of R1 is unknown, because the instruction I1 is still getting executed. At this point, can I go and fetch the data for I2? If I fetch the data, I will not get this latest value of R1, but some value of R1 that was computed earlier. So I have to wait till this addition completes. If the addition not only completes, the addition actually, the result of this addition is stored back into the corresponding destination register, namely R1 in this case. Until this addition stores back the result, I cannot go and fetch the data for this multiplication. If I do that, then I will be using the wrong value of R1 and not the latest value of R1 that is output by this instruction I1. So the answer to this question is no, because when R2 and R3 are getting added, we cannot fetch the data for I2. We have to wait for the I1 to finish its write back stage, wherein the answer will be available in R1, and then you go into the data, then you get this latest value of R1, and that is what this program, when you look at the program has a syntax and a semantics. Syntax essentially means the grammar. Semantics, the grammar basically says that this is the destination register and these are the source register, while the syntax says that there is while the semantics says that this is an add operation and this is a multiply operation, and these are the values of these that needs to be multiplied and added. So the semantics of this program essentially says that I need to go and use the latest value of R1 that is output by I1, and for that reason this particular instruction I2 has to wait till R1 finishes. So where should the I2 wait? It should wait at the decode stage till I1 finishes, then only it can start fetching the data for its operation. So essentially that means the pipeline is stopped, is temporarily halted, or we also call the exact word that is used is called stalled. The pipeline is stalled. Why it is stalled? Because there was what we call as a data dependency. There is a data dependency. The data dependency is because of this register R1. So something that stops the pipeline, it does something which will degrade the performance of the pipeline. Hence this data dependency is called a data hazard. So the data hazard is one that actually caused that pipeline to stop or wait for some other event to happen and then proceed. What is this dependency? This dependency can be also called as raw dependency. What is raw? Read after write. I am reading a register R1. I am reading that register R1 after writing into a register the same register R1. I am reading from register R1 after writing into this register R1. So this is read after write. So and that is why this acronym RAW comes here. So when we go on for building a pipeline, the architecture, when we go on for building a 5-stage pipeline architecture like this, everything would not be a very free flow. There are instances where the pipeline needs to be stopped, the pipeline needs to be stalled because of hazards, and one such hazard that I have mentioned here is the data hazard caused because of a data dependency, and that dependency can be also called as read after write. I am reading a register R1 after writing into R1, and since they are close to each other, meaning one after another, I2 has to wait at least 2 stages, because when I1 is executing, data cannot be fetched. When I1 is writing back, again data cannot be fetched. So after I1 writes back, then only the R1 can proceed. So at least 2 stages I2 has to wait. It cannot just follow I1. It has to wait for at least 2 stages before it proceeds in the pipeline. And this is called data hazard. Yes? There is a question? VTKIT, can you ask your question?
Hello.
Yes.
Sir, Aiko is coming along with your lecture. Some other faculties also teaching on the same.
I can't hear you. Your voice is very blurred. Can you just
Echo is
repeat
coming,
and
sir.
stop? Hello? Can you please repeat your question?
I have typed the message in my chat, so please go through it.
Can you type it on the chat
Sir,
window?
there is an echo of some other tutor that is coming along with the lecture.
Okay.
Sir, there is echo coming along with your lecture. Already typed, sir.
Echo of some other class is coming. Please resolve it. Mute your mic. Can you please type it in the chat window? Is it a technical question or something related to audio video? Echo of some other class is coming. Please resolve it. Yeah, I have told my technical team they will try and resolve it. Please mute your mic. Please mute your mic. Now is the echo coming? You can't answer because you have muted your mic. Please type in the chat after you mute your mic. Is the echo coming? Please type in your chat. Okay. Still you have not mute your mic. Please mute your mic, please.
आदित्य सर पढ़ा रहे हैं.
Okay. So the next hazard that we will be talking of suppose let us have a code like this. Suppose I have a code like this where I am doing multiplication of RT. I am comparing R1 with R6. If R1 equal to R6, then I go back and do a multiplication. I go back to L1. Otherwise, so I go to L1, else I go to the next instruction. Let me call it L2 here, else L2. Now, you can immediately see the problem here. So let me call all these instructions as I2, I3, I4. I1 is fetched. When I1 is fetched, when I1 is decoded, I2 is fetched. When I1's data is fetched, I2 is decoded, I3 is fetched. When I1 executes, I2 is fetched, I2's data is fetched. I2's data cannot be fetched. So I2 waits. because it has to compare R1 with R6 and you are writing into R1. So there is a read after write hazard here. So the I1 waits, I2 waits in this stage till I1 completes, then I2 starts executing, I2's data is fetched. When I2's data is fetched, I3 is decoded. Should I fetch I4 or should I fetch I1? Suppose I fetch I4. So please understand, first I1 was fetched, then I1 was decoded, I2 was fetched, I1's data was fetched, I2 was decoded, I3 was fetched. When I1 executes, I2's data cannot be fetched because there is a read after write hazard here, there is a data dependency here because I1 is writing to R1 while I2 is reading from R1. So I1 has to wait till I2 has to wait till I1 completes. So I2 waits. After I1 completes, I2 fetches its data, then I3 gets decoded. When I3 is decoding, should I bring I4? If I bring I4, then if this is equal, I should have fetched I1. So if I bring I4, then what happens here? I have done a wrong instruction, I have fetched a wrong instruction. If I fetch I4, then I have fetched a wrong instruction, I should have fetched I1. Why I have fetched a wrong instruction? Because if R1 equal to R6, I should have gone to L1, meaning I should have fetched I1. So after I3, should I fetch I1 or should I fetch I4? This will be known only after this instruction is executed. Before this instruction executes, I can't even decide whether should I fetch I4 or should I fetch I1. So the moment I find that this is a branch instruction, I have to wait till it gets executed for me to go and find out which is the next instruction I should fetch. Incidentally, what will happen is I will know that this is a branch instruction only when I decode it. So when I am decoding, I would have fetched some other instruction, say I4. So I have to go and cancel that fetch. So I will stop that that instruction. I will erase what I have fetched, and then wait for the branch to complete. Then only fetch the branch instruction to complete execution. Then I will fetch. So essentially, your next instruction to be fetched after a branch needs to wait for at least 3 stages. Again, that means your pipeline is stalled. This time it is stalled because of a control instruction or control transfer instruction. What do you mean by a control transfer instruction? This branch is called a control transfer instruction because it has the potential to change the flow of execution. What is control in a program? The one that dictates the flow. It says this is the next instruction to be executed. So first to do I1, then do I2, then do I3. So there is a flow. There is a flow of control which essentially says this is the next instruction to be executed. Now that control is basically modified or changed because of this branch, and that is why all these branch instructions are called as control transfer instructions. And now, since the pipeline stalling is because of control transfer, so this particular stalling of the pipeline or the hazard that has been caused to the pipeline is called control hazard. So we have seen two hazards this morning. One is called the data hazard, another is called the control hazard, and both of these have caused the stalling of a pipeline. Essentially, it means that the pipeline has to remain idle, or some stages of the pipeline have to remain idle till execution of some other instructions are completed. And because of this, the performance of the pipeline is basically degraded, and because of this degradation you see a less utilization of the hardware, but you cannot actually help much, because the thing is of prime importance is the correctness of execution. If I don't handle these hazards properly, then my execution becomes incorrect. The first thing in a processor, in a CPU, in a computer organization is that I need to build a computer that executes a given program correctly. Then comes the performance and other criteria. And so keeping that point in view, there is no use that I have a computer or a CPU that executes wrongly. So I need to handle these hazards, and I have to live up with some of these hazards. Let me also talk about another hazard before we wind up the discussion on pipelining. So just to recap, we have seen data hazard, we have seen control hazard. Now we are going to see another hazard called structural hazard. Now the operands that we have seen so far, we said multiply R1, R2, R3, add R4, R5, R6. So what are these R's? They are basically registers. What are registers? Registers are nothing but some temporary memory, temporary high speed memory inside the CPU. They are temporary high speed memory inside the CPU. They are also called as scratch pads, because you write some temporary results inside and erase it once you don't need it. How do these registers basically get the data? They get the data from the memory. So let me just give a small C code and describe how the C code is translated, so that you understand how the registers and the memory actually work. Let us say I want to do A equal to B plus C. That I have a C program which is int A comma B comma C. So let me write a small C program to explain you this. Moment this program is compiled and loaded into memory, there will be a space, an address allocated for the integers A, B and C. Note that in C, each of these variables, each of the integer variables are 4 bytes in length. So let me just assume that A is allotted the locations 1000, 2003. B is allotted the locations 1004, 2007. C is allocated the location 1008, 2011. Now the code for this would be load into register R1 the content of 1000. Or because I have to initialize this, okay, move into register R1 0, store the content of register R1 into location 1000, move into R2 value 5, store in 1004 the value of R2, add R4, R2, R1 and store the result of R4 in 2008. Okay, so move R1 comma 0 and store R1 into 1000 takes care of A equal to 0. Move R2 comma 5 and store the result of R2, store the content of R2 into 1004 will take care of B equal to 5. Then add R4, R2 comma R1 and store the results of R4 into 1008 will take care of C equal to A plus B. Now let us see what is happening. Let me call this as instruction I1, I2, I3, I4, I5, I6. So let me just write again here. Note first I1 is fetched. When I1 is decoded, I2 is fetched. When I1's data is fetched, I2 is decoded, I3 is fetched. Now between I1 and I2 there is a read after write hazard. This is writing 0 into R1, this is reading R1 and storing into 1000. So I2 actually waits till I1 completes, then I2's data is fetched, while I3 is decoded, I4 is fetched. Right? Now please understand that there can be a scenario where I2 is getting executed. There can be a scenario where I2 is getting executed, sorry, when I2's results are getting stored back and I4's data are being fetched. For example, this is not a correct scenario. Let me just for the sake of argument, just for the sake of example, let us take this. Load suppose I have a load instruction here which is reading from memory while there is a instruction which is writing into memory. Let me assume that I2 is in the write back stage. This is writing into the memory. While I1 is in the data fetch stage, this is reading from memory. Then there is another instruction which is fetched from memory, also reading from memory. So please look that there are three instructions. One instruction is writing into memory, one instruction is reading from memory the data. For example, I have a store here, I have a load here. The store is writing into memory while load is reading from memory, and this instruction, namely this store, is actually fetched from memory. I always read instruction from memory. So there are at least three instructions which are currently under execution in the pipeline that access the same memory. So the memory organization, which we are going to discuss in the subsequent classes, the memory organization should be in such a way that it can handle all these three requests concurrently or simultaneously. If it is going to handle each request one after another, this notion of pipe essentially becomes null and void. If I say I will handle I2, then I1, then I3, that means this has to wait for two stages for fetching, while this has to wait for one stage, one cycle. So all these three requests of this writing into memory, this reading from memory, this there is an instruction that memory, all these three requests has to be handled concurrently. If they are not handled concurrently, then the memory will essentially, the total operation will actually become sequential, wherein this instruction waits for this and this instruction waits for these two, or whichever priority in which you are going to handle this, right. So if more than one instruction tries to handle, tries to access the same resource, namely in this case memory, and because of that there is a stall in the pipeline, because the same resource cannot cater to three, and so it will make one fellow wait, then that hazard is called a structural hazard. I repeat, there is a shared resource and several instructions to access that shared resource at the same point of time, and this resource is not capable of handling such many requests, and because of that some instructions are asked to wait before proceeding in the pipeline. That type of a hazard is called a structural hazard. An example of that is memory, wherein there are three instructions. One instruction is writing into memory, another instruction's data is read from memory, and another instruction is fetched from memory. So, and then there are three memory requests to the same memory module, and if it cannot handle all the three, say we can handle only two, then it will ask one instruction, essentially causing the pipeline to stall. and because of this stall of pipeline, what essentially your performance degrades. That which actually stopped the pipeline is because of the structural organization of your system, and hence it is called a structural hazard. So what we saw in today's class are some of the bottlenecks in implementing a pipeline. We saw the control hazard, we saw the data hazard, and we saw the structural hazard. I will conclude this class by stating, beyond this, you will learn many things about building a pipeline in a computer architecture. We will be covering as a part of this set of lectures because we have other things to cover in the next 7 lectures. So I will just conclude by saying that for data hazard, the way the hardware handles it is using something called operand forwarding. You can Google and find out. These are not big rocket science, these are straightforward, but we don't have the time to handle this in this short span. So I suggest that you look into your textbooks, ask your teachers, or look into Google wherever you are comfortable with, and just understand what is operand forwarding and how it alleviates. It cannot totally remove the effect of a data pain of this data hazard. Similarly, for the control hazard, there is something called branch prediction. For structural hazard, you handle it with multi-ported resources. For example, I will have a 3-ported memory. 3-ported memory means that there will be 3 ports using which you can read or write data into the memory. And if I have 3 ports, then one port can be used for the instruction, another port for data fetching, and another port for writing into memory. So if I have 3 such ports, then this basically becomes very interesting. Okay. Right. So this is all about pipelining. In the next class we will start discussing about memory organization. I hope you have started looking into the tutorials. Please take the tutorials very seriously. Many things I teach are asked in the tutorials, and there are many more that are not taught here. I want the background material, some amount of background material plus some advanced material. We have put some questions in that, so that at the end of the 15 lecture series with the tutorials, if you had solved many of the problems in the tutorials, then I hope that you will have the satisfaction and you will have the at least some amount of awareness in the basics of computer organization, and I could also sign off with the satisfaction that I have done something good to you. Okay. Now I open for questions. Yes. Yes, please ask your question. DCRU. Please, please. We are not able to hear you, DCRU. We are not able to hear you. Please unmute your mic. what is the difference between static and dynamic pipeline? There's nothing to my best of my knowledge, I don't know whether there exists something called static pipeline, but there is something called static instruction scheduling versus dynamic scheduling. Static instruction scheduling means that the handling of these hazards, namely data, control and structural, will be done by the compiler. So the compiler will find out that there is a data dependency between instruction I1 and I2, and it will say that I2 cannot execute till I1 completes its write back stage, or I2's data cannot be fetched before I1 completes its write back stage. So the compiler will deduct this hazard and it no ops. No op essentially means a no operation. So if you take an instruction set architecture, there will be an instruction called no op. This no op is basically used to tell the CPU don't do anything in this cycle. So the compiler itself will detect that there is a data hazard and insert no ops so that the hazard is taken care of. So the hardware is very dumb. The compiler takes care of this handling of these hazards. This particular process or this particular mechanism is called static instruction scheduling, where the compiler particular resource to a particular instruction at a given point of time. So this instruction scheduling, if it is handled by the compiler, then it is called static instruction scheduling. So just mapping on your question, your pipeline doesn't do anything about handling hazard when the program is in execution. That is dynamic essentially means when the program is in execution. When the program is in execution, since your pipeline does not do anything, we may call it as a static pipeline. But the actual origin is static instruction scheduling, the compiler takes care. In this case, the hardware is very dumb. But on the other hand, if the hardware is very intelligent and the compiler is dumb, the compiler doesn't take care of any hazard handling, while the hardware detects that there are these hazards and it handles on its own, then that is called dynamic instruction scheduling, because which instruction is assigned to which stage of execution happens when the program is in execution, and that is why that word dynamic comes there. So if there is dynamic instruction scheduling, then that pipeline can be called as a dynamic pipeline. To the best of my knowledge, I am not seeing terminologies as static pipeline, dynamic pipeline. Maybe some book has it, but this is my interpretation to your question. If, to repeat and sum up, if the instructions are scheduled, or these, in other words, the hazards are handled by the compiler when the program is compiled or when the program is static, then it is called static instruction scheduling, while the hazards are handled by the hardware when the program is in execution, that is when the program is dynamic, then it is called dynamic instruction scheduling. Thank you. How does CPU knows about the data type of any variable by the instructions you have told us during structural hazard? Why should the CPU know about data type for handling structural hazard? I don't understand why the CPU should know about a data type during structural hazard. Can you please clarify? You can send an email to us and we will handle it. Okay. So you just say please send email. I don't understand your question, rather I don't understand why a data type, what a data type has to do with a structural hazard. This is a question by CSPIT. Okay. Right. Any more questions? Last question, another 2 minutes. Okay, now it's clear. GCT? Yeah, please ask your question.
Can you give an example to show a situation where hazards coexist? Hazards.
Where hazards?
Coexist. That is data hazard, control
What hazards?
Simultaneously exist.
Yeah, I think I showed one. Very simple example for this would be the control and data hazard coexist. Unless I know the result of this comparison, I don't know whether this is going to be equal to or not. So the result of the comparison is when this instruction writes back the result into the flags register. If you take any architecture, there is something called the flags. The flag, there will be a equal to flag, there will be a overflow, carry flag, etc. Now unless this particular instruction writes back into the flag register, I don't know whether this is going to be equal to or not. So this is going to write into the flag register while it is going to read from the flag register. So there is a read after write control as data hazard that exists here. And then obviously there is a control hazard, because when I fetch this when I fetch this instruction, should I fetch this or should I fetch L1? Because it depends upon its execution. So there is also a control hazard at this point. So a data hazard and a control hazard coexist at this point. Am I clear?
Sir.
Okay. Thank you very much. The next class has to start. So any other doubt, please send email to QEEE and I will try and answer as many questions as possible. Thank you. We will meet on Friday. Please revise and come. Please do the tutorial sheets and come, because from now on the classes will be highly interdependent. So if you don't know what was covered in the previous class, if you are not revised, then the next class would be Greek and Latin. So if you don't know Greek and Latin, so please do study and come. Please do revise the lectures. We have uploaded the videos. Please do view the videos and then come for the class. Lot of homework is necessary to attend the next set of lectures. Thank you very much.